whom I have known for over 30 years. He is presently Director of Central Road Research Institute. He was Deputy Director at IIT Roorkee before joining CSIR, CRRI. He has been Morth Chair Professor on Development of Highway System in India at IIT Roorkee during 2013 to 17. While his contribution in the development of highways is immense, as Director of CRRI, he has played a crucial role in the development of steel slag road technology. AI-based road safety solutions for Nagpur, third-party quality evaluation of Dwarka Expressway, promotion of usage of industrial waste in road construction, and providing solutions to road infrastructure development in border areas. He received Pandit Jawaharlal Nehru Birth Century Award from Indian Road Congress and Outstanding Teacher Award of IIT Roorkee, Date of Indian Road Congress, and convener of PCD 6, Bitumen, Tar and Other Products Committee of Bureau of Indian Standards. With this introduction, I leave it now for you, Manoranjan, to take this forward.
Thank you, sir. Thanks for that uh, very rich introduction. It's a matter of great pleasure to be part of this IRF webinar and moderating it. Very important and apt theme which has been chosen: sustainable alternate industrial waste materials for infrastructure development. The work has started, say, since 1990, but there has always been question like what are the various challenges, and out of all these industrial wastes, like which are the wastes which have merit and availability to change the ecosystem of infrastructure development. And today we have three outstanding speakers. One, Dr. Bhupinder Singh, who is a assistant professor at IIT Jodhpur, Mr. D. Satish Kumar from JSW Steel, and Sri U.K. Guru Vittal, who has been a chief scientist superannuated from Central Road Research Institute, worked extensively on usage of various waste materials for road construction. So we have three speakers, those who have rich experience, expertise in this particular, say, theme of the webinar. And before I invite the speakers for making a presentation, I would like to introduce them one by one. So Dr. Bhupinder Singh is an assistant professor in the Transportation Engineering Division of Civil and Infrastructure Engineering Department at IIT Jodhpur. And he worked earlier at NIT Jalandhar, NIT Patna. Recently, he visited University of Nottingham, UK as an Shire Fellow. He has 6 years of teaching experience and very active member of Indian Roads Congress and Institution of Engineers India. Currently, he is guiding 6 PhD students and involved in multiple research and consultancy projects. Our second speaker, Mr. D. Satish Kumar, is General Manager Research and Development at JSW Steel, Vijayanagar Works. So he is currently the group leader for Steels, Mills, Product Development and Waste Utilization Research Group. His research focus has been in modeling and simulation of steel making and rolling processes, and has expertise in physical metallurgy and thermomechanical simulation of steel. He has contributed significantly to slag processing and recycling and developed technologies for waste utilization and its sustainable usage in India's largest integrated steel plant. He is a recipient of the National Young Metallurgist of the Year in 2007, SAIL Gold Medal, co-author 2012, Golden Peacock Innovative Product Service Award 2016, 2023 and 24, and National Energy Efficiency Innovation Award 2021, NMA Award for R&D, Iron and Steel 2023. He has authored a number of papers and filed 25 patents in steel making, rolling and processing areas. And our third speaker, Sri U.K. Guru Vittal, He has been a former chief scientist and has 35 years of R&D experience at CSR CRI, New Delhi. So he worked in various R&D and consultancy projects in the field of waste and marginal materials, rural roads, ground improvement, technical audit of road projects. He has published and presented more than 100 research papers and authored over 85 technical project reports. Sri Guru Vittal contributed to formulation of several guidelines, specifications published by Indian Roads Congress and Bureau of Indian Standards. His work has been recognized through awards received from CSIR, Department of Science and Technology, Government of India, Indian Geotechnical Society, then Indian Roads Congress. So I welcome all the three distinguished speakers for this webinar. So we shall have presentations of all the speakers one by one. And so we have allocated 20 minutes. After all the three presentations, we'll have a brief question and answer session. So without taking much time, now I invite Dr. Bhupinder Singh, the first speaker. And besides our three speakers, we have many attendees, those who have joined online for this particular webinar. A warm welcome to all of them. I understand there is great enthusiasm, interest today in highway sector, the professionals. And the title of this workshop is very apt. The second part of the IRF webinar title, like out of the many industrial waste, which are the one which are good, which has the merit, and also availability for usage in road sector. Of late, we have seen steel slag has been very popular. In CRI, we worked on flyers, we worked on zinc slag, copper slag, and also currently using the red mud alumina. So personally, I believe that like if you work diligently, all of these industrial waste with good amount of processing, they can be put to use for civil infrastructure development. I'll close my remarks with that. And I now invite Professor Bhupinder Singh for the presentations. So please stick to the time.
Yes,
And
sir.
you can share your PPT.
Thank you, sir. I'm sharing my PPT. Sir, is my screen visible? Okay.
Yes.
Okay. So thank you so much for such a warm introduction and
Dr.
warm.
Bhupinder, sorry, the slide, it's not in full screen mode.
So now is it?
Means I can see it slide by slide, not in full screen.
Okay, sir. Just give me a minute, and I'll share again. So is it in the full screen mode?
Mr. Satish, no, it's not. It's not.
Okay, so just give me a minute.
So you have operate share screen, through share screen only you are doing.
Yes, sir. I'll share the screen. I'll share entire screen, sir. Then I
Yeah,
think.
I think that will work.
Yes, sir. So is it okay now?
Yeah, it's now good.
Okay.
Please
Thank
go
you.
ahead.
Thank you, sir. Thank you. So I'll start by thanking IRF for giving me this opportunity, and good evening to all the respected panel members and all the audience members who are present here to listen to this webinar today. So the topic of my webinar is utilization of recycled concrete aggregate in bituminous mixtures. As sir has already given my introduction, I am currently working as the assistant professor in the Department of Civil and Infrastructure Engineering at Indian Institute of Technology, Jodhpur. So let's start with the presentation. Coming to the brief introduction about what CND waste is and how it is generated. Uh, First, we will take a little a step back, and we will see okay, why this the utilization of all these industrial waste is required in today's time. So we all know that road construction is an economic development as well as the social development. As my supervisor, Professor Praveen Kumar, says in his lecture that roads for a country is like the veins in a human body. So like veins in a human body takes the blood and all the other nutrients from one part of the body to the another part of the body, and those are very important for the development of a body. Similarly, roads are also like serve the same purpose for a country. So if we see that from that point of view, that roads construction is a plays a major part when it comes to the economic development and thus for the social development also. When we talk about the road network in the world, then we have the approximately second largest road network in the world, and we are just behind USA. We are in front of China when it comes to the length of the road network. And in 2060 Morth report, it cited that there is approximately 6.22 million kilometers of the road length that is there. Since 2060 we are again constructing road at a very high pace. So in this figure, which we have taken the data from the NHI, you can see the highway construction like rate per year has been increasing since 2050 to 2020. It has been almost like more than doubled, because in 2050 it was around 1500 kilometers of highway that we were constructing. Now in 2020
Yes,
we
how many
constructed
on
pardon.
56/2 मेरा नाम लिखा है, मनोरंजन।
Okay. Okay. So now in 2020, it is approximately 4,000 kilometers of the highway that we are constructing. So if we see the road network that we have in India, so almost 90% of these roads are the flexible payments, and out of this flexible payment, most of the roads are the bituminous road, which construct the asphalt concrete top. Now, when we talk about the bituminous concrete or bituminous mixture, then bitumen is just below 10% of the total mix composition, and aggregates are like above 90%. So aggregates makes like most of the proportion of the this asphalt mixture. Although it is good that we are constructing a road network at a record pace, and which is the requirement also, but it comes with some of the problems. And what are the problems? One of the problem is the non-availability of good quality aggregates. In most of the country, in some part of the country, the availability of good quality aggregates is very difficult, and even if those aggregates are available, if we like consume too much of them, then that causes the depletion of the natural resources, because for the production of these natural aggregates, very environmentally harmful like quarrying and blasting functions goes on. So that is not good for the environment. So that is why that is a major concern, and that is the major challenge that construction industry is facing nowadays. Now coming to the another problem which we are facing nowadays, that is the production of the construction and demolition waste. So a waste material which is produced during the construction, renovation, rebuilding, modification, expansion, repairing and demolition of the building and other infrastructure is called construction and demolition waste. When we talk about the construction and demolition waste, then it is composed of like many factors, which contains the aggregates also, concrete, bricks, wool, glass, plastic, broken asphalt, and metals. Means whatever the things that you will find in a building, all those things are present in the construction and demolition waste. But if we see, the major chunk of this construction and demolition waste is the concrete that we get out of it. Now, this figure, it shows the construction and demolition waste that every country is generating in the year 2017. So here we can see China is generating a lot more construction and demolition waste, and the next country is India, and then the USA, and some of the Western countries, which is the France, Germany, and UK and Brazil are there. With the Western country, one advantage that they have, the deposition of this construction and demolition waste and the recycling is very high. So most of their construction and demolition waste gets recycled. But when you talk about the India and China, then the rate of recycling is very low. In fact, in India, disposal is also very poor. Not proper disposal is there, and whatever gets properly disposed also, the recycling is again very low. So some of the problems which gets generated due to that is that for the disposal, if we take it to some dumping yard, then that consumes a valuable land, and land is very precious nowadays. Then the another problem which comes due to the improper disposal, or even with the proper disposal also, that it causes the air pollution also, land pollution also, and due to the leaching, groundwater pollution can also happen. So these kind of problems are associated with it. Now another a new kind of problem which is not we don't usually associate with the construction and demolition waste is the disaster. So there are two instances which I'll be reporting here. One is we all remember that in 2050 Chennai flood, devastated Chennai flood came, and that killed approximately 500 people, and it also displaced around 1.8 million people. One of the factors which uh, increase uh, the intensity of that flood was the construction and demolition waste. Actually, there was improper disposition of construction and demolition waste, and then that C&D waste gets into the sewer system, and then it chokes it. So it choked the sewer system of Chennai. So that is why the water could not drain out from the areas, and then the intensity of that flood increased, and that caused the loss of so many precious lives. And then another in such incident was like reported in the China, where an illegal construction landfill collapsed, and which claimed 75 lives. That is also in 2050. So this is again, if it shows that if the proper disposal of construction and demolition waste, and not only disposal, the utilization is not done, then it may cause some of the disasters also. So now come to the we are coming to the topic of this presentation, which is the recycling of C&D waste, and then reusing it for the construction purposes. So recycling, for the recycling of C&D waste, again, recycling waste, C&D waste can be used in many fields. People have used it for the geotechnical applications, means for the ground improvement purposes. For geopolymer synthesis also people have used it. For seawall foundation people have used it. Landfill cover, it has been used, which has been reported in the literature also. And alternative pipe backfilling material also people have used it. But in this presentation we will be like concentrating on the use of the C&D waste in the asphalt mixtures, because that is what my research area is. So coming to the recycled concrete aggregate, what is recycled concrete aggregate? As we talked, that most of the portion, a big chunk of the C&D waste is old concrete blocks that are generated. So if we recycle those concrete blocks and get the aggregates out of them, then that is called the recycled concrete aggregate. So when we see any recycled concrete aggregate, it contains natural aggregates, which we can see here, and then there is a layer of adhered mortar, which is because it was part of concrete, so there will be some mortar which is still attached to those aggregates, and that is what you will find in any recycled concrete aggregate. Now people have used this recycled concrete aggregate in the unbound pavement layers also, cement concrete and bituminous concrete also. Now, what are the advantages of using this C&D waste to replace some of the natural or virgin aggregate? That is, first is the preservation of the natural resources, because it replaces some of the like virgin aggregate. Then the requirement of the virgin aggregate goes down, and due to which preservation of the natural resources happens. Then, if we compare the energy consumption in the production of the C&D waste and in the production of the virgin aggregates, then we will find that production of the RCA, or recycled concrete aggregate, consumes less energy as compared to producing virgin aggregates. And because again we are not consuming the less energy, then the harmful gas emissions also is low in case of recycled concrete aggregate. And there are many cost benefits are also associated with recycled concrete aggregate. But what are the disadvantages? The major disadvantage which comes in recycled concrete aggregate is because of this layer of adhered mortar which is attached to the aggregates. because of this layer, what happens, it forms a not a very strong bond with the aggregate. So when the load comes over it, it breaks down, and then that reduces the overall strength of the mix. It has higher water absorption also, and it reduces the aggregates specific gravity also. So due to which it is generally seen that these recycled concrete aggregate have inferior properties as compared to our virgin aggregates, and they do not, in some of the conditions, they do not pass the requirement which is given by the like authorities, like in case of road construction, whatever the specifications which are given by the MORTH, these recycled concrete aggregate, they do not meet it. So there is the problem. Now moving on to the production of the RCA. So I'll go fast in this. So first, this CND waste is generated. So there are two sources of generation of this CND waste. First one can be the artificial source, which comes through the construction and demolition practices, and second one is the natural source, which comes because of the disasters. So earthquake, flood, cyclone, because of this, a lot of CND waste is generated in a very short period of time. So when we get this CND waste, then this CND waste is like a large chunk of concrete. Then we do the primary treatment. It means we break it down into some of the manageable pieces, which you can see in the second figure. Then from there we get the crushed CND, construction and demolition waste. Then the secondary treatment take place. It means we try to remove the layer of that adhered mortar, because that is the problem, or we try to reinforce the layer of that adhered mortar on its place. So that is how secondary treatment take place, and finally we get the recycled concrete aggregate out of it. Now there are many methods of the treatment of that RCA. So first type of methods, which comes under the category of removing the adhered mortar. We want to remove whatever the mortar which is present on the aggregate surface. So first treatment type is thermal. So we remove the adhered mortar by heating it up to a very high temperature. So due to that heat treatment, what happens, because the coefficient of thermal expansion of aggregates and coefficient of thermal expansion of adhered mortar is different from each other. So because of that, some thermal stresses develop, and then adhered mortar gets detached from the surface of the aggregate. Second one is the mechanical and most common one. In mechanical method, we use some of the mixture, or in the laboratory we use the LA abrasion machine also. So we use the abrasion and attrition techniques to remove that adhered mortar which is present on the aggregate surface. Then in ultrasonic methods are also used. So first we dip our CND waste into the water, and then we apply some of the ultrasonic waves, and due to the application of these ultrasonic waves, the mortar gets removed from the surface. Then people use some of the acid soaking techniques also. In that we prepare the acidic solutions, and we like soak our CND waste in that. So then acid reacts with the hydration products which are present in the mortar, and then it gets removed from the surface. Second type of treatment processes are like reinforcing the adhered mortar on its place, so that it doesn't get detached when the load is applied on the aggregate. So then there are different treatment which are used for this one also. Carbonation treatment is there. Then use of cementitious or pozzolanic material. We treat our aggregates, these recycled aggregate, with the cementitious or pozzolanic material, so that adhered mortar gets reinforced at its place. Then in when specifically when we are using this aggregates for the asphalt mixture purposes, then we coat these aggregates with the help of the bitumen emulsion also. So because of this emulsion, when we apply, so it obstruct the pores of RCA also, and it improves the bond between adhered mortar and those aggregates also. So that solves our problem with the detachment of this adhered mortar in the mix also, and then it also reduces the your also reduce your water absorption, because pores gets clogged up. So then incorporation of the liquid silicon resin also people have used, and nowadays MCP bacteria also people use. We apply the bacteria on the aggregate surface, and these bacteria produce the calcium carbonate crystal, and these calcium carbonate crystal they improve the bond between adhered mortar and concrete. So these are different methods people have used. If we see the characterization of RCA, then physically we see they are very highly absorptive in nature. They have lower density, they have high impact value, higher abrasion values, higher crushing values, and they are rough, porous, flat, and irregular in shape. If we see the chemical characterization, then you will find that SiO2 content is really high in our aggregates, these recycled concrete aggregate, and which is a problem when we from the asphalt mixture point of view, because we have seen that aggregates which have higher SiO2 content in them, then they are poor in making bond with the asphalt binder. So that is the problem. Coming to the microscopic characterization, so you will see that the surface area of RCA is much rougher as compared to the natural aggregates you will find. So these are the characterization of RCA. Now moving towards the modification of the, so people have used different modification techniques, and they have combined also different techniques, as we have discussed, physical, mechanical techniques, and thermal techniques, and uh, acid soaking techniques, and they have found that uh, these techniques work really well. So you can see the specific gravity have increased in most of the cases, water absorption has gone down, and abrasion value has also gone down. So it contains from acid soaking to pre-coating with the slag cement, and to the calcium carbonate precipitation and MCP, and all those kind of treatment methods people have utilized. Now what is the effect of using RCA in asphalt mixtures? So people have found that there are different because RCA is such a like variable in the nature, because we don't, in most of the time, whatever the RCA we are collecting, we don't know about the history of that concrete, from where that concrete is coming, and what are the specification of that concrete is. So due to which you will see that in each of the uh, like uh, properties that we are talking about here, you will see some of the studies they have found RCA to be really improving those properties also, because what happens in some of the cases, these particles, RCA has some of the unhydrated cement particles also, so they get hydrated in some of the cases, so due to which they improve the performance also, and that is what we have also found in one of our studies. RC has the rougher surface area also, so due to that rougher surface area also, what happens, the interlocking gets better in some of the cases. So due to which you will see in the Marshall stability, people have found that if you are using the RCA above 50%, then the Marshall stability values goes down. And the researchers have also found that up to 50% people have, researchers have used, and they have found that it improves actually Marshall stability. Similarly with the ITS also, so people have used here, the opposite trend was seen. We have did the survey of more than 20 30 10 studies, and they have found that up to if we are using it above 20%, up to 20%, it was seen ITS values were going down, but in some of the cases people were using it for up to 30% also, and it was fine. And similarly the case was there for the rutting also, for the fatigue also, and for the resilient modulus values also, and moisture susceptibility and low temperature performance also. So in each of these cases people have found that in some cases it improves the properties, and in some cases it decrease the property. So from here the problem which is primarily associated with RCA comes into the forefront, that there is too much variability in RCA whatever we are collecting. So that is the major problem. That is why field implementation is also not getting much traction at the moment. Now there are
Dr. Bhupinder,
yes sir,
how much time you will require?
sir, I'll just take 1 minute and I'll conclude my presentation
Yes,
here.
yes, please.
Yeah. So there are different treatment methods also people have used, like the calcination process, pre-coating, reason also to activate RCA. Then MCP is there, pre-coating the RCA with the bitumen emulsion, using the lime, and many of the studies have used cement also, because cement is a very popularly used filler material in the asphalt mixture also, and it is easily available also. So many of the studies have used cement also to coat the aggregate and then use it in the asphalt mixtures. So that way they have found that it has performed really well. But there are some problems which are associated with the RCA. So we have used that RCA can be used, and there are some of the methods also, treatment methods, using which we can improve the properties of the RCA and asphalt mixture also. But at the moment, the problem is the variability in the RCA quality. So currently there are no standard treatment methods which are there for the RCA treatment. There are no like mixed design method which is there for the RCA. And because of all these like confusion, I feel that practitioners are still like hesitant to adopt it in the like field. So that will be my like concluding remark. And these are all the mm, references. And thank you so much, sir, for giving me
So
this
thank
time.
you, Dr. Bhupinder. And please stay connected because we'll take up all the question answers towards the end. So I request all participants to post their questions. They can post questions on the chat box so that at the end of the third presentation, you can come back. You can address to the queries. Thank
Sure,
you. So
sure, sir. Thank you.
now we move over to Mr. D. Satish Kumar from JSW Steel. So Satish ji, over to you for next 20 minutes. Thank you.
Yes, sir. So, hope it is full screen.
Yes, yes.
Okay. Thank you, IRF, for this opportunity. Thank you, Mananjan sir, for introducing and doing this. In this sustainable alternative industrial waste material event, I am representing from iron and steel industry, one of the biggest manufacturing domains in any country which comes in. For every ton of steel, we generate huge amount of slag, dust, and sludge. I would say, let's say for every ton of steel which is being produced, almost 700 kgs of solid waste is being generated. And this disposal and recycling is really a concern for the steel makers. Parallelly, there is a requirement from the civil industry for a lot of aggregates and solid materials. The presentation, what I'm showing you today is kind of a marrying between the two industries and how the waste of one industry can be utilized effectively and sustainably in other industries is being shown. Now, in this approach, all these steel makers have now started developing a lot of processing technologies of these waste which has been generated. And we are going into some kind of an integrated waste management system in all these steel plants. So I'd like to show a few examples also into this. But again, when I say that we want to recycle the material, we want to reuse the material, the word sustainability comes into picture. The sustainability is not, the word sustainability has a quite broader umbrella. It not only encompasses the application, but also has to take care of the economics of the disposal. So you cannot simply dump it, but to find out some way, some means by which it can be economically converted into an application. So when I say sustainability, there are two parts of it. First is the technology part of it, and usability, and second part is the economics. The examples what I'm going to share it with you today actually takes care of both and makes a good business opportunities for a lot of prospective entrepreneurs and a very win-win solution for both the steel industry as well as to the construction industry. Normally, when we see the steel plant, it has a huge cycle, starting from the iron ore, what we receive, we beneficiate, then agglomerate, then iron making, then steel making, then rollings, etc. And there are so many wastes being generated at different points. During beneficiation, we generate a lot of tailings, then dust at a lot of places, sludge at many steps of processing, then slags, and then the scales. Now, if you see these quantities, what we are talking about, the biggest component among all these is slags. I would say if slag is taken care, almost 75 to 80% of the total waste generated is been taken care to this. When I say these wastes are being generated, we need to actually understand them by putting them into certain groups. We see that we can put them into two categories. Tailings and slags are one type of category where you have maybe a little bit lower iron, but higher silica and alumina, whereas dust and sludge has mostly contains higher iron. So most of the technologies which has been developed in iron and steel industry basically direct the dust, sludge, and scales to recycle back into the process of iron making, steel making. But the tailings and slags are the kind of the byproducts which are basically seen to be used outside the iron and steel making process in some other industries. That's the basic concept of all the waste which is being done. Now, let me tackle one by one on this tailings and slags. To be taken care. Tailings is nothing but what we generate as a byproduct during the beneficiation process. We get a lot of low grade ores. We have a step of beneficiation in it where we upgrade the iron ore from particular value to a higher value, and then the gangue is separated out. They're normally wet in condition and normally used to be stored in large tailing ponds, etc., which end up in a lot of issues sometimes when when its bund breaks, etc. Now the new technologies have come up where we use it as a press filter, we dewater them, and then we use it back in mine backfill. This is a very interesting application which has recently come up, where this the dry disposal of these materials have come up, and because of the concerns of the mining industry of rehabilitation and reclamation, etc., take place, the tailings has come up to a very good solution to build and maintain those mines which have been left out after the sufficient mineral has been taken out. Coming back to slags, normally slags are generated in two steps: iron making and steel making. And again, in steel making, there are different types of slags into this. And if what I will be showing you in broad categories is that all these slags which are generated from iron making, steel making process normally comes in molten state, and they are processed differently based on different technologies. But finally, what we are trying to claim is that all these slags can be converted into fine aggregate as well as coarse aggregates. Both can fit to match the specifications of both fine aggregate and coarse aggregate and fine aggregate, which are being used in all the construction applications. I will share many of the examples starting with this. When I say we generate two types of slags, the iron making slag and steel making slag. If we see till now, not much of these slags were getting utilized. Maybe what I'm saying is till 5-7 years back, and a lot of interest has come up from both sides to convert them into specified aggregates, and then the acceptance of these aggregates by the by the construction industry also. So iron making slags normally are granulated, and it used to go for cement making. But over a period of time, with increasing capacities, that is iron making slag also is getting accumulated by steel plants. Steel making slag normally used to get dumped because of its own inherent properties of containing iron. It's non-cementitious. And if you see, go to any big steel plant, you will find mountains of these slags lying over past few decades being stored there. And today we have a solution by which it can be converted into aggregates. Coming to iron making slag, as I said, most of this is normally granulated and used for cement making, and a part of it which is not granulated normally used to get for landfilling and dumping. And what has been done recently is that especially this granulated iron making slag, which looks like river sand but has never been utilized into as a fine aggregate or a replacement of river sand. What we have done here is we tried to investigate that what could have been done to this granulated blast furnace slag and convert into fine aggregate. We made a comparison with river sand. We find that granulated blast furnace slag was having lower density and lower specific gravity, higher water absorption. Those were the primarily reasons by which it has tried but never been commercially utilized for being used as fine aggregates. At JSW Steel, we developed a technology by which we changed the granulation procedure during the iron making process by changing the water temperatures. We utilized a vertical shaft impactor, a multi-deck screen, and finally what came out was a process granulated blast furnace slag from a granulated blast furnace slag. And you can see in these pictures that how the shape and morphology has been changed from a very irregular, highly porous structure to a more uniform and rounded pieces, which resembles more close to the iron making slag. And once it was compared, we find that this process granulated blast furnace slag could be 100% replacement to the river sand which is being used in the construction industry. And that's how at JSW Steel Vijayanagar Works, we set up the India's first iron slag sand plant. And I would say for the last 7 to 8 years, more than 3 million tons of this manufactured sand or granulated blast furnace slag sand has been sold in and around Karnataka, Kerala, and Tamil Nadu, etc. That's a very, very ideal example of converting waste into a product. Recently, we are also developing a technology by which this granulation process, which used to happen with water, which was one of the reasons for highly porous material, we developed a technology for dry granulation of these materials. Now, by doing a dry granulation, I'm getting a more rigid structure, and these fine aggregates can be utilized and find it more useful, more rounded directly, and a lot of processing steps can be avoided. So this is also a development which has been done from the iron and steel industry to convert these wastes into products which can be sustainably utilized in other industries. So dry granulation is kind of a future technology which is coming for iron and steel making people, especially for granulating this blast furnace. This during iron making process, we also get some amount of coarse slag or solidified slag in the pit which comes out. This can also be processed and can be utilized either as coarse aggregate, or we can crush them and utilize them as fine aggregate. We have done both these exercises at JSW Vijayanagar Works and in NH67 Hospital Bellary Road. A lot of this crushed dry pit slag from blast furnace has been utilized in the road construction. We also crush them to very fine pieces, and a fine aggregate has also been made using this material. These technologies are now commercially established and running at Vijayanagar Works. Coming to steelmaking slag always has an inherent issues because of its expansion behavior, which comes from the free lime and the free MgO which is present in it. It also contains certain amount of metal. It has higher density, it has shape is quite irregular, and that's why it never attracted the attention of construction industry for being used as an aggregate. Over a period of time, a lot of solutions have been developed to age these materials, starting from natural aging to dry and wet aging to open steam aging, even pressurized steam aging and steam box technology. Even chemical stabilization of these slags have also been developed. These are the kind of technologies which are being developed in-house at many steel plants around the world. And these technologies make this slag conducive and matching to the specifications of the construction industry for these aggregates which is being used. Now, these are additional steps which is being adopted and commissioned in many of the steel plants, including JSW Steel, where we are trying to convert these waste, avoid dumping, and convert them into products to be used. What we have done at our place is we try to crush them very fine, and we find that the expansion behavior, which if it has to be used as a coarse aggregate, where we need to do a lot of aging steps to be involved to convert them into product. We crush them and make it very fine, where its expansion behavior significantly reduces, because the free lime and the free MgO which is present in it, which are expansive in nature, when they come in contact with water, gets removed. This process step, the process has been developed in such a way that those fines are being sucked and removed, and that's how the world's first steel slag sand plant has been established at JSW Vijayanagar Works, where we started converting our steel slag into steel slag sand from this unit. This process is a little different than what used to make sand from our iron making process, where the fines was not an issue. Here, the fines was a bigger issue. So we have adopted a dry classifier where the fines were sucked, removed, and that's how we get two different products out of this whole process. The patented process by us, where we get a sand, a little bit of higher density sand for use in civil construction, and these fines which can be used in cement and agriculture. And that gives a complete solution, end-to-end solution for this huge amount of slag which is generated in steel plants, which normally used to get dumped, is now getting converted into products for construction industry. If we compare the test results of these aggregates, what we have done, we find that compared to river sand, both iron making slag and steel making slag individually gives better results because of higher density and its more controlled shape. And in combination of these also gives us a good result. So it can be used individually as well as or in combination with either of them to be used. And you can see both in mortar as well as in concrete, the 28-day strength of these products are higher than the control sample of the river side. That's how at JSW Steel we established a 1500 tons per day iron slag manufacturing unit and a steel slag manufacturing unit, first of its kind in the world, at single location, being where the waste is being converted into a very useful product supporting the construction industry. Now these fine aggregates are way ahead, and we always call it eco-friendly because the river sand comes from rivers and the M sand, which is normally used, come from mountains, and they both impact the environment. Whereas this is the one which is eco-friendly, available throughout the year, and very consistent composition coming from the iron and steel making process. These have been tried at various agencies, including CRRI, and it has been found that it can be used for almost all applications, starting from buildings, paver blocks, plasterings, highways, all applications. Even we started using it internally. Iron and steel making units are very heavy industries. We make steel coils of almost 20 tons, 30 tons, 40 tons of coil weights, and you can see the floorings and all the other construction areas have been built using these slags, and they have been working there for many years, taking these heavy loads also. We have also specifically started using them in roads, because roads is one of the specific areas where a large amount of these slags can be consumed, both in coarse and fine form, and all different layers it has been experimented. We also tried at NH67 Hospat Bellary, as I've shown you, and has been done using electric arc furnace slag and blast furnace slag, etc. But what most important thing which has been done in the recent year is all steelmakers were doing this slag for utilization in their own domain. Recently, when Ministry of Steel and CRRI came together and worked on a project, on a national project for developing guidelines for this steel slag, that's how a lot of clarity came in, and CRRI has recently released these guidelines to be approved and used as in roads during the month of May. And the most important part, I would say, which is there is this table which came up, which clearly mentions and gives guidelines to all the steel makers as well as to the users, which has come for the first time, I would say first time in the world, where Mr. Satish Pandey and his team has worked and come up very clearly that what should be the limits for BOF, EF, and CONARC type of slags, what should the permissible limit, and what kind of test methods should be utilized. Some with this very clear specification available, it opens this door for utilization of these slag aggregates, both in coarse and fine form, in road applications. The key points which has come up from that study, where we were also a part along with other steel makers, where there could be reduction in the bituminous road thickness. There could be conservation of around 80,000 tons of natural aggregate for every construction of 1 kilometer of 6-lane road. Reduction in the cost coming up because of the slag being utilized, durability is improved, and finally we can say that the greenhouse gas emissions is also reduced because the use of these aggregates. Very aptly, these things have been shown in that report, where that as compared to conventional concrete road as well as conventional asphalt road, there could be significant reduction in the overall thickness which can be brought in for the same load applications in both the roads. CRRI and Satish Pandeyji's team has also demonstrated taking slags from our steel plants at various locations in the country, where on-site applications have been demonstrated, starting from Hazira in Gujarat, then Dolvi in Maharashtra, in Northeast, at many places, and these roads have been tested and have been working very aptly matching to all these specifications. Apart from this,
sorry,
yes, sir.
It's time to wrap up. Maybe
yes, I'm just finishing in another 30 seconds.
Thank you.
So apart from these applications, we have also working, especially the steel making sites, working on rural roads where you don't use too much of bitumen or concrete roads. The slags on its own has their own hardening behavior by carbonic or hydraulic reactions. Mixing of steel slag and iron slag along with an activator simply acts as a good bed for rural applications. This has been tried at many places inside our plant at the construction sites. Apart from this, we are also working on developing stone blocks and breakwaters using the slag aggregates. Many testing have been done with many agencies, and we have been using them at some of the areas at our coastal plant in Dolvi. They have been found to be very good applications where basically these big stone blocks are not available, and this waste slag can be converted into these kinds of applications. Another interesting application which is coming up is the railway ballast, where these aggregates have been found to be useful. This is also under study, and we hope that these new applications will also come up very soon and will be utilized in large proportions from the slags which are generated by iron and steel plants. Finally, what I conclude is that, especially from the steel perspective, we have taken a fresh look to minimize these waste, but also we are also looking into a zero waste concept where we want to utilize it 100% into certain applications. And the examples what I have shown that how slags can be converted into aggregate for this construction applications is a very good example of converting waste, not just converting it into some product, but converting it into a wealth, which gives a clear definition of sustainability in terms of application as well as economics coming into picture. Thank you very much. That's how I end my presentation.
Thank you very much, Satish. In fact, we'll come to the question and answers after the third presentation by Mr. Guru Vital. So, while closing, then I'll share my remarks. So, welcome, Sri Guru Vital ji. I think you could not join in the beginning. So, where we have introduced all the speakers. So, I also introduced about you while we started the program. So, means a warm welcome to you, and you can start your presentation. Please share your presentation. After your presentation, we'll have a combined question and answers for all the three speakers.
Okay, sir.
So you have 20 minutes, Guru Vital ji.
Yeah, okay, sir.
Yeah.
Is my screen visible?
Not the presentation. We can see only the files.
Okay. Is it visible now, sir?
No, it's not visible. It says UK Guru Vital has started screen sharing. Double click to enter full screen mode.
Okay. Let me try once more.
You have to share the entire screen.
Yes, sir.
You can see the slide, but you have to make it full screen.
Is it now full screen mode, sir?
No, it's not full screen. The slide is there.
Actually, I have given my slides to IRF. They can share it now. Share it because it is proving difficult for me.
If you are connected, can you share the PPT shared by Sri Guru Vital? Anyone from IRF technical team?
Yeah, IRF, they can share the screen. I can make the presentation.
Okay, sir. Just give us a second. We are sharing.
Yeah. Thank you. Okay, thank you. So my presentation is with regard to various industrial ways that CRRI has been working over the past few decades in using them and trying to use them in road infrastructure. Next slide, please. Next slide. Please change the slide. Yeah. So at the outset, let me thank CRRI because I worked in the CRRI for many decades and my colleagues also. Now, coming to various different types of industrial ways that we have investigated and used in roadworks, fly ash will have to take the first place because it's the quantum of production and utilization is the maximum with regard to the different industrial ways. Presently, we are producing around 150 million tons per annum, or 175 thermal power plants are there, and about 80% of the ash is being used, out of which 25% goes to PPC production and another 20% into the roadworks. This 20% for the roadworks, it keeps changing annually. But PPC production is almost same, continues to be same, continues to increase also. This road works utilization is mainly in the form of a fill material. Next slide, please. Please change the slide. Next. Yeah. So this fly ash, of course, it can be used in various ways in the roadworks as a fill material for the embankments, as both reinforced as well as unreinforced embankments. You can use it in pavement works also for flexible in the form of stabilized layers, and in the rigid pavement as a admixture with cement concrete pavement. We have to stabilize this, characterize the waste materials, and it is a fly ash has been accepted as an environment tested also and accepted also as a environmentally safe material. It is having so many various favorable properties: lightweight, higher shear strength, and easy to use in the field. And even when it is raining, we can we can roll that fly ash material. So so many favorable properties are there. So it is being widely used. Please go on. Next slide. This slide I have just put to show that whatever the different properties of fly ash with different types of soil, just to show that it is in a way similar to the soil. Fly ash is in a way similar to the soil, but some of the properties definitely changes. For example, if you look at this optimum moisture content, it will be little bit higher when compared to the soil material. But when we look at this angle of internal friction, that will also be higher. Even though OMC is higher, we usually associate higher OMC with clay soil, but here phi value will also be more. So this kind of a similarity as well as dissimilarity with the conventional construction materials will always be there, not only with fly ash, with all other industrial waste also. This point is very important. That's we have to know, keep always in mind. Similarity and dissimilarity with the conventional material will always be there, and accordingly we will have to use the industrial waste in our road application works. Next slide. Please change the slide. Yeah, this is the manner in which the fly ash embankments are constructed. In the center of the embankment, we use this fly ash, either the bottom ash or the pond ash type. And then, of course, we will be providing a side earth cover, and on the top also another earth cover, and which will also act as a subgrade soil also. And in this way, many of the industrial waste we will be using it in the embankment in this manner only, because almost all the industrial waste except maybe one or two like a phosphogypsum, they don't have cohesion. They don't have cohesion, but they have got very good friction angle, but they don't have cohesion. So if we construct an embankment without providing the side earth cover, there will be erosion. Erosion due to water, erosion due to wind, etc., etc. So that's why to prevent that erosion, we will have to provide a protective earth cover, maybe 0.5 meter, maybe 1 meter, 1.5 meter, depending upon the height of the embankment. If the height of the embankment is more, earth cover with thickness required will also be more. If the height of embankment is lesser, less thickness of cover will suffice. So this kind of a cross section is also similar to different types of industrial waste, including fly ash. Next one. Next slide, please. So on this one particular project I am telling, this is Wazirabad, the signature bridge, which is very famous. You all, many of you, most of you would have seen that. And when this bridge was being constructed, you can see in the first photograph, that was the condition. So much of waterlogging was there. It was a low-lying area just by the side of the Yamuna River. So much of waterlogging during flooding used to take place, and that water used to remain there for months together. And in that particular location, we had the embankment had to be built about 10.3 meter high unreinforced embankment of fly ash, and above that they have another 6 meter high reinforced embankment has been constructed. So in this manner, in such a you can very well imagine what can be the bearing capacity in that particular stretch. So much of water is there. So this material proved to be an ideal material because it is lightweight. And second thing is that it worked out very economically also. Otherwise, to bring a Muram type material and back dump it into this gravelly type material and back dump it into the water, it would have cost almost 2 times for this bridge construction. So all those problems were solved by using fly ash. So next slide, please. Next slide. Yeah. These are some photographs. So the construction, as you can see, it is similar to the earthen embankment construction. Same type of machineries we will be using, and quality control tests, etc. They were also exactly similar manner. So then in that manner, of course, the all other industrial waste also similar. Whatever the construction machineries that we use for conventional material, conventional construction, same type of machinery will have to be used. Only maybe in one or two rare cases, little bit of modification may be required, but that is not the rule. That generally we use the same type of machinery, same type of construction methodology also. Next one. Next slide. So at that time, of course, some apprehensions were raised whether this will be environmentally safe. So we conducted the environmental tests also. And as you can see from this slide, that whatever the properties, whatever the heavy metal contents is there in the fly ash samples, it is similar to earth also. Next one. Next slide. We can construct the reinforced fly ash embankment also. Whatever the case study I showed you is an unreinforced embankment. And for the reinforced embankment, fly ash is a better type of fill material when compared to this silty type of soil. So silty type of soil, of course, we cannot use in reinforced earth embankment. And whereas this fly ash, because it is having very good permeability, because it is having very high phi value, it is the most ideally suited material for reinforced embankment. Next slide, please. So now this kind of guidelines are also available for stabilization as well as this embankment construction also from the Indian Roads Congress. Next slide, please. Waste plastic is another important material investigated by the Flexible Pavement Division of CRRI. And for this also, of course, we are having IRCSP 98, which gives very good details about how to use this waste plastic. Next slide. There are two different processes for using waste plastic. You all know that, dry process and waste process. We have to shred the waste plastic. We have to clean the waste plastic, shred it into a size so that it passes 2.36 mm. And depending upon whether we are adopting a dry, mostly this guideline is for the dry process only. Wet process, we have not yet brought any guideline. And so it is used in the dry process. Next slide. These are the manner in which the waste plastic is being shredded and readied for mixing with the bituminous mix. Next slide. When we use the drum mix plant, of course, there may be chances of waste plastic getting burnt out, and so a special arrangement is to be made for feeding the waste plastic to the drum mix plant. If you use the batch mix plant, of course, this kind of problems will be easily be solved. There will not be there. Next slide. Another guideline brought out by Indian Roads Congress is with regard to slag usage. Of course, this guideline, they named it as, which is applicable for the rural roads. Now, of course, the CRRI has come up with the guidelines for using steel slags in the highway sections. Also, it is under discussion. In these guidelines, we have copper slag as well as iron and steel slags also. Both have been dealt. Next slide. Some details with regard to copper slag. Copper slag is we get at two locations in our country, Dahej and Tuticorin, and this material is similar to sand, similar to coarse sand, and so that's why it will be having a very good phi value, very good permeability, very good CBR, etc. But of course, the one point which we'll have to look into, which we'll have to keep in mind, is that it's very heavy. It is having some iron content. When copper is extracted, iron will be left out, and so its specific gravity will be more. Its density will also be more. So that point we'll have to keep in mind. Next one. Next slide. So test sections were constructed by CRRI and they were monitored on NH sections for this embankment. You note that previously, as I told, the embankment is to be constructed using the waste material in the core of the embankment, and the side slopes are to be protected. Next one. Next slide. This is with regard to C&D waste. Of course, this is the IRC guideline, IRC 121, and BIS code. In formulation of these guidelines and codes of practice using C&D waste, CRRI had a major role to play. Next slide. When we use C&D waste, the important point is to process that waste. The fly ash and copper slag, such type of industrial waste, we use it in a major manner as such, as available. But the C&D waste we need to process. That's because you can see from the photograph that as it is available, C&D waste, what photograph shows that it's not, we cannot make use of that material because it's very heterogeneous. So we'll have to crush it, sieve it, bring it into a perfect, in a acceptable gradation, not uniform gradation, acceptable gradation, and then we use it. So these are the other three photographs. They show that the processed C&D waste. So how it looks like that, the coarse one as well as the finer variety of the C&D waste. Next one. So we constructed the test roads using the C&D waste. This one for embankment, this pavement construction, pavement widening in Delhi for this colony roads. So we used it as a stabilized cement stabilized layer. Next one. These are some photographs, cement stabilization. The already existing pavement was there, blacktop you can see, and the road was being widened. And in the widening portion, we used this material with cement stabilization, and of course, it worked very well. The C&D waste has got very good properties. If it is to be, if we are going to stabilize it, we're using a additive like cement. Next slide. And in the another project was with where we used it in a DDA road in that was near Bakkarwala in Delhi, North Delhi, and there the issue was that the water table was very high, very close to the ground level, and it was a kind of a slushy area, daldal jamin jo hum kehte hai, so slushy area, and in that area we had to excavate that slushy soil, backfill it with a good earth, and then construct our road. So the backfilling portion with a good earth is a very costly process. So instead of that, we successfully used C&D waste. Next slide. So this is the photograph, how the road area that looked like, and when after excavation, and then this crushed C&D waste being used and compacted there. And next slide. Then the road was built. You can see the finished road section, and it has given very good performance without any settlement, without any rutting, without any uneven problems are there. And so that shows that If we look at our quality control aspects, etc., whatever the waste material is there, that can be successfully used. Next slide. Next is with phosphogypsum. This is a waste material from the fertilizer plant. This is available at many locations in our country. This also CRRI has worked. My colleagues, Dr. Anil Sinha and all, they have worked on this material, and we have constructed a test track also. This material, specialty of this material is that, yeah, it has some gypsum. So that's why when water is added to that and compacted, it hardens. It hardens. So this material, when it hardens, that's why the CBR value is very high. UCS value, unconfined compressive strength value, is also quite high. Next slide. These are some photographs of that test road construction, and as you can see from this photograph, the test road it's performing very well. Actually, in that test road, very heavily loaded trucks were plying. Very heavily loaded trucks, which used to bring material to the plant and take back the finished fertilizer. They were playing on that road, and this has successfully withstood heavy truck traffic. Next slide. Red mud, this is also available in a few states like Jharkhand, Odisha, etc. It's a bauxite tailing waste from the alumina production, and this material is also, of course, from environment point of view, we'll have to use it in a careful manner, and this also has been very successfully tested in our laboratory. Next slide. Marble slurry dust is another important material. We have so many marble quarries in Madhya Pradesh, in Rajasthan, etc. When we extract marble, this slurry is produced, and when the slurry hardens, dries up, we get the dust, and this dust, marble slurry dust, is a huge headache for this industry, and okay, sir, headache for this industry too, and this can be used in our roadworks. So next slide. Next slide. In the similar manner, Gerofix, which is a waste material from the zinc tiling. Next slide. Next slide. Kimber, waste material from this diamond mining industry. Next slide. Processed municipal waste, which of course we get in any city area. So all these materials have been successfully tested, characterized in the CRRI, and many test sections have also been built, and the performance of these roads, test roads, have been successful. Now, next slide. So now just 1 or 2 minutes I'll take and complete my presentation. The stepwise procedure for using the local material. I'm not using the word waste material because it's not a waste material. It is a resource material for our road work. So let me use the word term local material. So whatever the local material is there, like maybe a quarry dust, quarry waste, or quarry reject, fly ash, slag, C&D waste, etc. That first it has to be identified, which is available within economic lead from our construction road construction project, and whether it is available in the coarse aggregate form or in a sand form or a combination of these two, we'll have to find out. And if it is available in a coarse aggregate, we can use it as an aggregate in our WBM, etc., layers, etc. If it is available as a sand material, we can use it in our sub-base course, etc. The next thing is that characterize the material. What are the engineering properties that we'll have to find out? AIV and gradation, water absorption, flakiness. So these are with regard to aggregates, and if it is a finer the sand type material, we have to find the gradation, plasticity, Proctor test, and CBR value, etc. Next important step would be to ensure that environmentally an industrial waste material is acceptable. It will not create any environmental problems. It will not release heavy metals into the underground water or into the subsoil. So that has to be done, and we have very good protocols for that kind of environmental acceptability test. Next slide. So once we are through with all these tests, we can decide based on the we will have to decide whether we can use it as such or we can use it after improvement. So improvement means usually it will be stabilization. You finding the what is the mix that is required, maybe mechanical stabilization or additive stabilization like cement stabilization, etc. So these are all very well defined procedures are available. IRC SP 89 is there that can be referred to for taking up these works. Usually using this material in a wearing course will have to be a little bit more careful, because in the wearing course, as we all know, the stresses will be more, and so that we'll have to look into the those issues, and mixed design will also be done very carefully, entering an agreement with the generator supplier for the supply of generator for the supply of these materials. Next slide.
You have to wind up.
Yeah, this is the last slide, sir.
Okay.
This is the last slide. And payment design as per the IRC guidelines, rate analysis we have to do, DPR it has to be incorporated, and we go ahead with construction and performance monitoring, and definitely it can come into the guidelines like what are the guidelines that we have already shown. So this is the outline of the procedure that we need to do for some of the materials for which guidelines are not available. Thank you, sir. Thank you. Next, last.
Thank you very much.
Thank you.
So now we open up for question answer. Means before opening up, I'll say that like the three presentations were very important. Mr. Guruvittal has worked very extensively on these various waste materials while at CRI. Then also our colleagues at CRI are working. And obviously that has led towards development of various IRC codes, because that's the only document that gives support that increases the confidence amidst the users that yes, this material can be put to use. And JSW has demonstrated that like Mr. Satish Kumar gave great examples for infrastructure, not just roads, means not just highways, airports, but also like water breakers. Means there could be great range of applications. And Dr. Bhupinder Singh talked about the research. And Mr. Guruvittal said that these materials are going to be similar and dissimilar properties. So wherever there are dissimilar properties, that provides a challenge to carry out research on that. Dr. Bhupinder Singh, that he presented on usage of recycled aggregates for road constructions. So there will be a lot of properties, characteristics, which is not exactly fitting into the conventional material. So then you need to undertake a deeper research to make those modifications. So that's how they can be utilized. I have seen the journey of waste materials since 1990 to 2024, and we have seen many documents. And presently, we see greater application of these waste materials for infrastructure sector. Personally, I am very confident, and I'm sure that we work in a very regimented, systematic way, so that we can bring confidence of the users in terms of its deployment. So with that, I close my remark. So one of the attendee has raised a hand. Please introduce yourself. So from IRF team, please allow the attendees to ask questions. Or is it in the chat? Question answer, we can see. Okay. So can you read the question answer? Mr. Satish, Mr. Guruvittal.
Yeah.
So Aditya, your question is for Mr. Guruvittal. So Mr. Guruvittal, can you read the comment?
Yeah, the first comment is with regard to slag sand. Slag sand, do you recommend it for VDF flooring for the basement cost comparison? I request
Yeah.
JSW.
So point number one, anywhere wherever you are utilizing river sand at this moment or M sand, the slag sand can be utilized even for the VDF flooring also. Of course, non-expansive aged slag itself. Coming to cost, as we said, this cost has always been, till now, it has been much lower than the river sand cost. The cost implications only come from the distance of transport. But otherwise, the processing cost and the cost X works, I would say is less than 50% of the sand cost which is available in anywhere in and around the steel plants. So from cost wise, it's always beneficial.
Sir, the next question is with regard to this use of industrial waste. One of the participants, Mr. Aditya, he has raised the point with regard to this environment acceptability test. I would say that actually that as I mentioned, testing protocols, procedures, they are already in place. The Ministry of Environment and Forest, they have given clear guidelines. So what are the acceptable limits for the various heavy metal content and what should be the testing procedures, etc. It's available there. And we have to go by that procedures. That's okay. But one interesting thing I would like to put you here is that the Jarosite and Jarofix. Jarosite is the waste material that is produced and it will be having a heavy metal content. It will be unacceptable to use it in as such Jarosite. But we fix that whatever the heavy metals are there so that the heavy metals do not leach out. So that process is also available. International experiences are there, and national experience are also there. So that process is available. So from Jarosite, we make the material called Jarofix. So Jarofix is now becomes an entirely acceptable material and it has been used. So in this manner, characterizing the material from the engineering point of view, characterizing the material from the physical properties point of view, and characterizing the material from the environmental point of view, all three are required, and we'll have to take a judicious decision based on the results of the test. Thank you.
Thank
And
you,
next
Mr.
question is for
Bhabia.
Satish.
Mr. Satish, there are a couple of questions which you can answer. There
Yeah.
are concerns with respect to pH value of the steel slag.
Okay.
So,
First is, let me answer pH. When pH comes when you add slag into water. Normally, we in slag or steel, we define it in terms of basicity. The slags normally have higher basicity than natural aggregates, but basicity we measure from XRF. That's why it shows high CaO, and that's how you call it as basicity. But this lime is normally present in combined form. I would say almost 95% of the lime present in this slag is in combined form, in the form of dicalcium silicate or tricalcium silicate, which will not separate out. First thing. There is 4 to 5% of free lime, which basically causes some amount of expansion in the slag when they are used as coarse aggregate. But while we are using for bituminous mixes in roads, top, etc., when you crush them very fine, they all are exposed. And rather, this presence of small amount of free lime is useful and gives you better strength when you use it in bituminous mixes. That has been proven, and there are so many articles on this. So from that perspective, I would say you shouldn't concern about the pH, seeing the CaO value of it because it is in combined form. Secondly, the free lime, whatever is present, is useful when you use it with bituminous mixes. Coming to the second question, that how do we prepare sand from steel slag? It's a process. Steel slag normally, when it comes out in molten state from the vessel where the steel is being made, it is put into pits. It has a mix of metal and slag. It is taken to a slag separation plant where they are crushed, and metal and non-metallic components are separated. This non-metallic components is then taken to the sand plant, where it passes through 3 steps. One is a vertical shaft impactor to crush them and size them to less than 4.75 gradation. Then we have a deck of screens which separates out in terms to fit into gradation of zone 2 or zone 3 as per IS 383. And third step is it passes through a vertical shaft, passes through a dry classifier, where whatever fines are generated during this process are sucked out, because the specification doesn't allow you more than 10% of minus 150 microns. So we remove that through this process, and that's how the final what comes out matches to the gradation what is given in the standards. That's how we convert whole steel slag into a sand process.
So, Mr. Gurvital, in fact, leachate of fly ash, that's a question. And how much percentage cement is used in C&D waste?
Yeah. Actually, when we go for this stabilization of this any of these materials, this C&D waste also, whatever the percentage of cement that we use will be similar to the soil material. Of course, it will depend upon what type of soil material we are stabilizing. If we are stabilizing a finer type of soil, it requires more amount of cement. If we are stabilizing a coarser type of soil, it requires lesser amount of cement to give a high UCS value. Same thing applies here also for this type of industrial waste materials. Now, specifically, you are asking for the CND waste. CND waste, as I showed you in my photographs, it has to be processed, crushed, and made into different gradations. And when we intermix those gradations, we will be having coarser particles also and finer particles also. Normally, about 3 to 4%, or at the maximum 5% of cement will be required for stabilizing the CND waste. And we can get, if we use a lesser amount of cement, let us say 3% of cement, definitely that whatever the UCS value that we'll be getting will be more than 1.5 or 2 MPa, and it will be very useful for this sub-base layer. And if we just add 3.5, 4%, etc., in the UCS value, it will go up to 3, 4.5 also, and even much more also at 7 days itself. So that's why it will be very useful even in the base course also, this CND waste. So that is with regard to CND waste. What is the mechanism of strength? It is same, cement hydration. So we get calcium silicate hydrate, and it binds the CND waste particles. So that's the same way. And with regard to this leachate in the fly ash, of course, it is determined by using this standard tests. And exactly the code number I am not remembering. I can send you, if you ask IRF, I will send you the IS code numbers for this leachate analysis that I will send you. What is the waste material?
Yeah, last question also for you.
Will the waste material, is it in the porous support water absorption for groundwater recharge at the road construction site? So this is a very interesting question. Actually, the groundwater recharging, can we use this waste material? Actually, this groundwater recharging is a very important issue nowadays for sustainable construction. I fully agree. And we have different types of specifications like porous bituminous mixes and porous concrete, which help in this groundwater recharging, which have been used. And sir, the varying course of a road pavement is what we construct, what we use as a waterproofing layer. Otherwise, the base course and the sub-base course, if it is granular, if it is bound with the cement, it will be, permeability will be lesser. But if it is a granular material, granular base and granular sub-base, the permeability will be very high. It will definitely recharge the water. But normally, actually, we do not wish groundwater recharging in the road pavement itself, because during the process of groundwater recharging, it will of course first of all saturate the subgrade also. So that is not a useful step. That's not an advisable step. So that's why the water has to be taken out, and then as you have pointed out, groundwater to be recharged by the it can be done at the site, but away from the carriageway. Now, for recharging, as I pointed out, the granular materials will be very useful. So CND waste, if it is crushed, fly ash, as well as steel slags, etc. Of course, once we have tested them for environmental properties, environmental acceptabilities, and we are sure that it is not going to discharge any heavy metals, we can use that. But certain materials like phosphogypsum, as I already told you, it will harden when it comes in contact with water. So that may not help. So, sir, my answer is that we'll have to be choosy while deciding the material for this groundwater recharge. Definitely industrial waste can help, but we'll have to be choosy. Thank you, sir.
Thank you. Thank you very much. Dr. Bhupinder Singh, any point you would like to make? Any finishing points? Please unmute yourself.
Sir, there are, I think, two questions which Dr. Rishi Chhabra has asked. One is, he asked what is the treatment method which is feasible in terms of cost. So in my opinion, we have also used the different type of treatment methods, which includes acid treatment also, thermal treatment also, and mechanical treatment also. So in our experience, this mechanical treatment works best. And from the energy point of view also, it works better. And from the cost point of view also, it works better. And then the
Okay.
second question is that RCA can be used in lab, but what about the availability of RCA when we are talking about the field implementation? So is it feasible from yeah, it is feasible. Currently, again, as I pointed out in my presentation also, the problem is because there is so much variability in the recycled concrete aggregate quality that we get. We don't have any standardized methods and standardized codes for the treatment of these aggregates. So once if that is available, then it can be easily treated in the large quantities also using some of the centralized plant, and then it can be used in the field also. Field implementation can also be improved. So thank you so much, sir. It was a very insightful presentations from Guru Vittal sir also. And thank you for making me part of this webinar. Thank you.
Thank you. Thank you. Mr. Satish, anything, any closing statement from you?
It's good that so many things have been done. It's an good learning for us that all the industries are working towards consuming these waste water generated, and I'm so privileged to see that CRRI has been working to develop methodologies of using them and converting them for various applications into the road. I guess if these things go forward, with so much of construction happening in India, these studies and this expertise which is available through these kinds of seminars will really help everyone. It's a good initiative. I'm very happy to be part of it.
Thank you, Mr. Satish. So we had three speakers, Dr. Bhupinder with academic research, Mr. Satish for actual application, Mr. Guru Vittal who has done a very systematic trial and also contributed towards development of codes. So all efforts are required, and that will certainly make a stronger case that will build confidence with respect to usage of all these industrial waste for the civil infrastructure development. So that's the only statement. I'm very positive, optimist that yes, these materials, they can be utilized very effectively for the infrastructure development in the country. So with that, thank you very much. Thanks to IRF for the opportunity, to me for moderating this session. And thanks all the three speakers, all panel, all other attendees for this IRF webinar. Thank you very much.
Thank you, sir.
Thank you, everybody.
Thank you. Thank you. Thank you.